You are having a puzzle sort of thing. Now we have our next speaker with us. It's my pleasure to introduce our next speaker for the session, Dr. Abhinav Kumar sir. He is from IIT Hyderabad. His research areas includes wireless communications and networking, green cellular networks, user network selection, device-to-device communication, radio source management in heterogeneous wireless access networks. He is also a senior member of IEEE. He is reviewer for various IEEE transactions like transactions on mobile computing, transactions on vehicular technology, transactions on wireless communications. So we are truly honored to have you over here, sir. Now I request Abhinav Kumar sir to address everyone.
Hi, good morning everyone. Thank you for the kind introduction. Thank you for inviting me for this particular talk. It's always a big pleasure coming to this place. I've been here once before, I think. There was a more technical talk. I've been told that most of the audience here are first and second year students. So I'll try to keep it as simple as possible because the topic is a bit advanced, cooperative relaying in OFDM and MIMO systems. So I'll try to simplify it as much as possible. Right. I believe you already attended a couple of sessions, one by Professor Swadesh Day, one by Venkatesh Garu from our Silicon Labs, and then a couple of other sessions also in and around this topic. But at the same time, we'll start from the very basic. At any point of time, if you have a doubt, feel free to raise your hand. I hope there is some sort of mic arrangement. We'll reach out to you and I'll try to answer. For whatever reason, if you're not able to ask in between the session, you can always ask at the end also. Either works, right? For my talk, I'll start with a very basic overview of MIMO. I do understand there has been a session on MIMO already yesterday. Nevertheless, just to reiterate the concept, I'll start from MIMO, give a very brief overview of MIMO. I'll not go into the mathematical details a lot because I know you guys are still picking up some of the basics. How many of you have done signal cell systems? Very good. Matrix algebra or linear algebra? And probability? Very nice. So you have that, then very nice. So you have the mathematical and the technical background to appreciate that technical content also. But I have tried to keep it as simple as possible because my motivation is to, in some sense, attract some of you to this domain, right? And that's one of the reasons I'm here. My prime reason of being here is you guys, to pitch this to you guys, right? So in the hope that some of you will get motivated and pursue higher studies, and out of that fraction, some of you may potentially consider IIT Hyderabad, right? That's the broader motivation of me being here. That being said, I'll share more about the institute if time permits toward the end of the talk, right? So I'll start with MIMO, some basics of OFDM. So I'll motivate why OFDM is important, what is the difference between OFDM and OFDM, and then how we can combine the two in the context of cooperative relaying. I'll also go into very brief basics of cooperative relaying, right? And then some future directions on what is currently happening, what is the state of the art in this domain from 6G perspective. Because now everybody has started talking about 6G. 5G is already available. How many of you have a 5G phone? 5G enabled phone? So nice. There are a lot of folks, at least some folks, 20% folks who have a 5G enabled phone already, right? So people are now working in the research domain for 6G. So I'll also highlight how cooperative relaying with MIMO and OFDM is now getting transformed from a 6G perspective. But very briefly, I'll do that. If you have an interest, I'll share my email address at the end. Ping me and we can figure out some modalities, how you can work within our group. Coming to MIMO, as already some even more learned folks before me or more experts before me might have explained to you, MIMO is essentially about multiple input, multiple output systems, right? Wherever possible, I'll take examples from real life to communicate, right? So in MIMO, we can have various kind of setups. We can have multiple transmitters at the transmitter side and multiple antennas, receiving antennas at the receiver side. And you can use it in various mechanisms or various fashions, right? There are various ways you can use it. Oops. Can you please change to the next slide? Maybe I'll request you. This one is not working properly. Sorry. Yeah, thank you. So for example, you can have some TXs numbered as 1, 2, 3, 4. Similarly, you can have RX 1, 2, 3, so on and so forth. The advantage of MIMO is that there is going to be a channel between each transmitter receiver pair. So for example, you have transmitter 1, receiver 1, there will be H11 between receiver 1, transmitter 1. Similarly, H21 between receiver 2 and transmitter 1. So on and so forth. You can write it as a matrix, right? And then there has been considerable amount of math that has been done to analyze the systems. I will not go in that direction, right? I don't want to demotivate you. I want to motivate you to this area, but I'll at least highlight what can be achieved and why this is useful, right? So for example, for MIMO, we can have spatial modulation or spatial multiplexing. Spatial multiplexing is where I am sending distinct piece of information on distinct transmitters. You can view this as 2 transmitter, 2 receiver pair. I'll give you a real life example. Let's say, I'll give most of the examples for folks sitting in the front rows. So let's say there are 2 gentlemen here. They are able to communicate in English. And somehow myself and your faculty, we know sign language. Hypothetically, I don't, sorry. But let's say we know sign language. Even if we are in the same room, do you think our usage of sign language has any implication on their verbal communication in English? No. Their usage of English has any impact on our communication in sign language? No. So same thing happens in spatial multiplexing. We are presuming that we have multiple paths. Let's say 2 transmitter, 2 receiver, H11, H12, H21, H22. And we are trying to send orthogonal symbols or symbols on these paths such that they don't have impact on each other, right? In some sense, they're orthogonal. We'll also see mathematically how we can convert it to an orthogonal domain by using suitable space-time block codes. Was space-time block codes covered yesterday? Space-time block codes? No? Okay, then I'll cover them. Good. Then that leaves some interesting, something new for you guys today. So now, keep this concept in your mind that we are trying to do spatial multiplexing where we want to pump in more data. Because if we are communicating in sign language and they are communicating in English, the total amount of communication happening is almost double. Because there are 2 parallel paths working, right? But instead of doing this, we can look at it from another perspective. Let's say there are two of us and we want to communicate the same piece of information, the two of them, right? One way to do this is I speak at one time and then madam speaks at one time and you try to understand. Another option is both of us start shouting at the same time in perfect synchrony. Then there will be amplification of whatever we are saying. Although the information is same, we are not trying to enhance the data rate. What we are trying to enhance is probability of success that you will be able to listen to this. Now, for this distance, this example doesn't have a lot of meaning. But let's presume I don't have a mic. And again, our two good friends here, they're sitting at the back of the room. Then, individually, I may not be able to communicate without the mic. But together, if we shout, there is a reasonable higher amount of probability, probability that they will be able to decipher what we are trying to say. And we can generalize this further. Instead of two people shouting in perfect synchrony, we can have 3, 4, so on and so forth. This property is called as transmit diversity, where we are trying to diversify in some sense the number of transmitters involved so that at least some of that information, it is the same piece of information, but at least some of it gets decoded, right? We can also take it back to the same example that we were using for sign language and for verbal communication. Let's say we are communicating the same piece of information, we are operating in pairs, right? 2 transmitters, 2 receivers, one using sign language, one using English. We communicate exactly the same thing, but on 2 parallel channels. So we are not increasing the data rate, we are trying to improve performance in terms of probability of successful detection. Or in some sense, we are trying to reduce probability of error, which is precisely what transmit diversity is all about, right? We can also have something called as spatial modulation, where we can say, okay, we'll choose who will transmit at what point of time. We have 2 transmitters, one using sign language, one using verbal communication. In one time slot, one will speak. In the other time slot, other will speak. So it's, in some sense, in spatial modulation, we are modulating in space. How many of you have done a basic course in digital communications? Digital communications? Analog communication? Analog communication. So you know modulation then, right? In modulation, we're trying to modulate a wave. What kind of modulation are you familiar with? AM? AM, FM, right? So spatial modulation is, instead of modulating the amplitude or instead of modulating the phase, we are modulating which transmitter transmits. This itself has information embedded in it, right? Again, this is not an exhaustive list of MIMO techniques, but these are some of the fundamental ones that we typically use. Now, I have given the example here for 2 cross 2 in some sense. You can generalize this to M cross M also. So instead of having 2 transmitter, 2 receiver pairs, you can have M transmitters and M receiver pairs, right? Theoretically, more the number of transmitters, more the number of receivers, more is the gain. Now the gain depends on what kind of technique you're using. Are you using spatial multiplexing? Then the gain is increased data rate. Are you using diversity techniques? Then the gain is enhanced probability of successful detection or reduced probability of error, right? We can also use a combination. It's not that we have to do only one. We can try to do a mix and match. We can design techniques which achieve certain amount of diversity gain and certain amount of multiplexing gain, right? But of course, as you might have figured out by now, there is a trade-off. Either you can communicate more and more information, or you can communicate less information more and more reliably. But you have to choose where you want to operate in this domain. Now this part that I have just presented to you, this is already being used for any smartphone in this room. If you're using a 4G smartphone, it already has at least 2 transmitter or 2 transceivers, I should be saying, in it. For the matter, the base station that you have, typically it has 8 to 16 antennas, 4G itself. Now as we are heading towards 5G, we are looking at massive MIMO, where we are looking at very large number of antennas. Again, most of those antennas are at the base station. How many of you have seen those Wi-Fi access points with 4 transmitters? Have you seen the box? You've seen, right? So that is again MIMO. We have 4 transmitters there because it gives gain. So that is why you must have seen the older Wi-Fi access points. They used to have 1 transmitter, 1 black antenna coming out of it, right? I'm forgetting the name of that antenna, but I presume most of you must have seen it. There might be one deployed in this room also. I don't know. Maybe it's not visible, which is good, but I think that's the one, probably. So you have typically one, and then in past couple of years it has increased from 1 to 2 to 3 to now 4. Very easily you can buy on Amazon or Flipkart a Wi-Fi access point with 4 transmitters. Same is true for your laptop or your phone also. Again, for Wi-Fi it will have typically at least 2 transceivers in your device, right? So it's not that this whatever MIMO we are discussing is some 60 kind of a concept. It's already there. We are already using devices in the market in practice which support MIMO, right? Now, on top of that, on top of diversity and multiplexing gain, we can also do beamforming using MIMO. What is beamforming? Beamforming essentially means, let's say you have one radiating element. It has certain pattern in which it will omit. You can have omnidirectional or you can have directional radiating elements, right? In this example, we have directional. So it radiates in this fashion, right? Now, if I take 2 of them, if I take 2 such radiating elements, I can, and at the end of the day, what we are feeding into the radiating element is a sinusoid. What you have studied for your modulation course, communication, basic analog communication course. You have a cos omega t plus theta, and you are modulating this. So each of this radiating element is getting an input which is a cos omega t. Now we can have 2 cos omega t's, one being fed to each radiating element, such that they have some phase shift, right? Now we can tune this phase shift to decide what is going to be the output of this main lobe. Should they add constructively? Should they add destructively? And also in which direction should they add constructively or destructively? Now this level of control is rather limited with 2 radiating elements, because you only have 2 cosines. You can only, so if you overlap 2 cosines, you can only have so much gain. But if I have more and more number of such cosines, the amount of peak that you can get is significantly higher. You mentioned you have done signals and systems, right? So you must have studied, there is this expression where you can obtain deltas by overlapping exponentials, complex exponentials in discrete time. Have you studied that? Delta in time domain infinite series is equal to delta in frequency domain. How many of you recall that? No? Please revise. Please go back and check. So there is this expression that you must have used where any discrete time infinite series of delta in time domain is equal to an infinite series of deltas in frequency domain. And that expression is obtained by adding an infinite sequence of exponentials, complex exponentials in one of the domains. So effectively, if you take sufficiently large number of exponentials, you can get a impulse at every repeated time period. In this case, this is a very smaller subset. So we are not taking infinitely many, we are taking finitely many, and that's why we are getting these peaks. More the number of radiating elements, sharper and sharper will be the peak, right? Now, not only this, we can also track users. We can also decide not only the value of this peak by constructively or destructively combining these cosines in each of the radiating element. We can also decide whether I want my main lobe to be maximum or the side lobe to peak out. So which is precisely what has been done here. The cosines, the phase shift has been such that this particular lobe becomes most prominent and the other lobes are becoming side lobes. So this way we can choose the direction and the amplitude in that direction of the beam. Why is this important? This is very important because in communication or in cellular networks, for example, one of the key bottlenecks is interference. So going back to our example of English and sign language, if we 4 were the only people in the room, life would have been easy. Then we can use sign language, English, and job done. But there are close to 100 plus people in this room. You can also think of it as 100 plus mobile phones in this room. If each mobile phone is to communicate with the base station at the same time, you all want to chat, you all want to download movie, you all want to do video conferencing at the same time from the same base station. Hypothetically, let's say you all have same service provider. Then how to support that? One way to support that is if we do beamforming so that individual users, so user 1 signal comes on, I'll call it purple, and this one is orange, and user 2 signal comes on the orange beam, right? So this way both the users can be served in the same time slot because their signals are coming in very directional fashion. So this directivity is very important, and this is how communication systems have evolved. For that matter, it used to be omnidirectional. When we were using 1G phones, omnidirectional phones. 2G again omnidirectional. 3G, it was directional at the base station. Base station had more number of antennas, phone didn't. 4G, it is directional both in the phone and in the base station. Base station has 8 to 16 antennas. User equipment also has at least 2, typically. 5G, it will be several number of antennas, because now we are, although it is not deployed yet, current version is not standalone version of 5G, but when millimeter wave comes into 5G, then you will have significantly large number of antennas in your phone itself, right? That can be used to create directional beams from your phone to the base station, and anyway it is already being used from base station to the phone, right? So we can combine this with all the previous things that we have discussed in terms of spatial multiplexing, as well as diversity techniques. We can also do beamforming on top. In interest of time, I'll quickly skim through these slides, but coming to the trade-off part that I was explaining, so there is a clean trade-off between how much gain you can have in terms of diversity and how much gain you can have in terms of multiplexing. As I mentioned earlier, you can only have maximum value of one of them. So we will operate somewhere here. So you must have studied pulse amplitude modulation, right? So if you're using PAM technique, you can either get a maximum spatial multiplexing gain of this with a 1x1 receiver, or a diversity gain value of this. I think it will be more apparent with 2x1 or 2x2 will be better. So for a 2 transmitter, 2 receiver pair, you can have maximum 2 spatial multiplexing gain. You can parallelly pump in 2 streams. Stream 1 of data on one transmitter receiver, stream 2 of data on another transmitter receiver. But then you can't have any diversity gain if you're using 2 as multiplexing gain. If you want any diversity gain, you have to reduce your multiplexing gain. For example, we can operate at 1-1. At 1-1, what is happening is we are pumping in one stream, but we are getting a diversity gain also of 1. I'll give you an example also, mathematical quick example I'll try to give. And similarly, I can have a diversity gain of 2 with 0 multiplexing gain. So there is no gain. We are sending just one information, but in both the streams we are sending it to maximize the diversity gain that we obtain, right? So again, you can ignore these parts. If you're not familiar, it's okay. But broadly, you can look at it as, so this is a very famous seminal work by Alamati. This opened the whole area of space-time block codes. Right? So it's a bit old paper, 1998, almost more than 2 decades now. But this is amongst the first works which proposed a technique to realize this diversity and multiplexing gain through a 2x2 system. So if you have 2 transmitter, 2 receiver system, how to obtain this gain in practice. That is what this paper proposed. And the structure is as follows. You have transmitter 0, transmitter 1, receiver 0, receiver 1, and these are the channels. H1 is the channel between transmitter 1, receiver 0. H2 is the channel between transmitter 0, receiver 1, so on and so forth, right? So you have 4 channels. Because you have 2 transmitters, 2 receivers, you'll get a matrix. H11, H12, H21, H22. Here, instead of H11, H21, H22, H21, they're calling it H0, H1, H2, H3. But it's still the same 4 channels, right? Now what happens is, for the proposed technique in Alamati's work, the technique is as follows. You transmit symbol 0 from antenna 0 in time slot t, symbol 1, S1 from antenna 1 in time slot t, and in the next time slot, t plus capital T is the symbol duration, you transmit minus S1 conjugate from antenna 0, S0 conjugate from antenna 1. Although it may look very simple, like you have 2 symbols, S0, S1, now you're taking conjugates and you're shifting their places, adding a minus sign. But there is a nice beauty to this architecture. It's very simple, but it's very impactful also, as we'll see in the next slide. Now, at the receiver, what is it that we are going to obtain? At the receiver, we are going to obtain 4 symbols, because there are 2 time slots and 2 receivers. So each receiver will obtain one thing in one time slot. 2 receiver will obtain 2 things, 2 receive symbols in one time slot. In 2 time slot, they will obtain 2 to 4, right? So the 4 received symbols will be as follows. At receiver So let's say R0 is H0 S0 plus H1 S1 plus N0, where S0 and S1 are coming because we are transmitting S0 and S1. So this is the transmitted symbol. The received symbol, how many of us read additive white Gaussian noise channel? AWGN? Not yet? Okay, no problem. N0 term is just noise. So don't worry about the noise characteristic. It is some noise that is getting added in the communication channel, right? Whenever we transmit something, it has to propagate a path. If I am speaking to you guys, the voice signal, it propagates this channel. What you receive is not identical to what I am speaking. For that matter, in this context, it is even difficult because I am speaking to this loudspeaker, it goes into the system, the audio system processes it, then there is a speaker somewhere, that speaker is communicating to you guys. So essentially what I am saying and what you are hearing at this point of time are not the same. There is some additional thing happening in the channel, which is precisely what this H0 and H1 characterizes. So if I have S0 transmitted here, it gets, or S0 star transmitted here, it gets multiplied with H1 and noise gets added to receive the signal. Same thing is happening with each symbol transmitted. So what we are getting is, for R0 it is H0 S0 plus H1 S1 plus N0, R1 is minus H0 S1 conjugate plus H1 S0 conjugate, and R2 is H2 S0 plus H3 S1 plus N2. Similarly, R3 is minus H2 S1 conjugate plus H3 S0 conjugate plus N3. Where the R2 and R3 are slightly different because instead of transmitting S0 and S1, now we are transmitting minus S1 conjugate and S0 conjugate. So that is why there is a minus sign here and a minus sign here and conjugate here. So these conjugates and the minus sign are coming because we are transmitting the signal in that sense, right? Now what is the advantage of doing all this? We are doing all this, but how does it help? It helps because at your receiver, I can multiply these symbols. Let's say at the receiver, I know somehow H0, H1, H2, H3. What I can do is I can obtain S0 tilde, which is this linear combination of R0, R1, R2, R3, right? If I take R0, this is R0. If I multiply it with H0 conjugate, what will happen is H0 conjugate into H0 will become mod of H0 square. It's a complex number, right? So you multiply conjugated value with itself, it will become mod square. So what I effectively will get is alpha 0 square plus alpha 1 square plus alpha 2 square plus alpha 3 square. All signal components in S0 tilde, which correspond to S0, they get added up. Please check the math. So I have anyway shared the slides. You can go through the math later also. So effectively what is happening is all S0 components are getting added up or S1 components are getting cancelled. We can pick one of them just for illustration. So for example, R0 has H1 S1, right? Now, where else do we have? So if I multiply it with H0 conjugate, this will become H0 conjugate H1 S1, right? But I also have a minus value of that sitting right here. So when I take this, for example, H1 R1 conjugate, the minus value and a conjugate on top, it will cancel out. So by construction, what we are doing is for S0 tilde, all S1 components get cancelled out. There are cross terms by design. Similarly for S1 tilde, all S0 component of the signal gets cancelled out. What remains is only alpha 0 square plus alpha 1 square plus alpha 2 square plus alpha 3 square, S1, and some noise components. But as you see, unlike the previous expression, the expression of R0, R1, R2, R3 had cross terms. There was one S0 term, conjugated or otherwise, one S1 term. But now we have only S0 terms in S0 tilde and only S1 terms in S1 tilde. Not only this, there is alpha 1 square, alpha 0 square plus alpha 2 square plus alpha 3 square. So in some sense, we are not only able to separate out S0 and S1, we are also amplifying them. Because now the signal component, because this is the signal, right? It is getting amplified compared to your cross term. Cross term is becoming 0. And now we can apply any traditional technique to detect it. How many of you have studied ML, maximum likelihood based receiver? Have you guys studied that yet? No, not yet. Okay. I'll briefly motivate or try to motivate it. So once you have S0 tilde, right? From in S0 tilde, if I know H0, H1, H2, H3, I know alpha 0 square, alpha 1 square plus alpha 2 square plus alpha 3 square, because they're essentially mod squares of HIs. I can subtract, and let's say it's a binary scheme. Binary scheme means S0 can be +1, let's say, and -1 to keep life easy. Now I can apply a rule on top that I will subtract from S0 tilde alpha 0 square plus alpha 1 square plus alpha 2 square plus alpha 3 square into 1 and check what is the value. Similarly, I can subtract from it, same thing, multiplied with -1. Whichever is minimum, it is going to be closer to my transmitted actual symbol S0, and I will decide in favor of that. This is very crude explanation for maximum likelihood based receiver. You will probably study it in more detail in near future. The idea is, if I am transmitting some information, I try to find what is closest to that information at the receiver and decide in the favor of that, right? So that way, this becomes much easier to analyze at the receiver. Now, purposefully, I have not gone beyond 2 cross 2 because the math is more interesting maybe for me, but more involved maybe for you guys, right? So this was just to motivate that if you have a MIMO system, it gives you gain compared to a CISO system, right? Which is precisely what these results indicate, that if you have your error rate, the error rate for 2 cross 2 systems are going to be much, much lower than the error rate for your no diversity, one transmitter, one receiver system, right? The results are all available. You can also, this paper itself is already available online. You can just check out the paper. The whole math has been taken from the same paper, LMT's paper itself, right? Now what has happened is, since that time, since 1998, when this idea was proposed in theory, this idea is already available in hardware. Any wireless device that you're using for Wi-Fi or for cellular is using something either which has LMT or a much better code than LMT. Because this was the first code, amongst the first codes, right? Since then we have evolved. If you look at from research perspective, there have been more than 10,000 research works in MIMO, which analyze the performance. Maybe at least 1,000 PhDs have worked in this domain since past 20 plus years, right? So it is a field which people have invested a lot, right? Now, what is the catch? There is always a catch. There are no free lunches. Like real life, in technology also, there are no free lunches. Now with MIMO, the challenge is, in theory, it appears if you have larger and larger number of antennas, you will get more and more gain. But that does not happen in real life. Why? Because here we assumed, or we make the presumption, that H0, H1, H2, they don't have any mathematical dependence, right? However, in real life, you can't find such channel. If I'm going to deploy here one transmitter and then one more transmitter, maybe these two will have very less correlation. I don't want to delve deeper into that, but let's say correlation. They will have very less correlation in terms of their channel, H0, H1, H2, H3. But if I start deploying in the same space, 100 antennas, then it will become very close to the order of their wavelength. And then for the same set of antennas, I will not find independent channels. There will start occurring correlation between their channel. The moment there is correlation, whatever math that we have done so far, that it nicely cancels out, there will start occurring cross terms, right? It doesn't work out as neatly as we have analyzed it. So it works well for 2 cross 2. If you have 4 cross 4, it may work reasonably well. But there is a number of antennas after which this gain starts diminishing, right? And that is why for 5G, there was a lot of talk 10 years ago about massive MIMO, that we'll use 40 antennas, we'll use 100 antennas. But it has not occurred. In real life, there are no products which realize this much gain, because each antenna deployment is costly. See, imagine your phone. When you have to deploy 2 antennas, you have to ensure the phone size remains the same. You have to put the chip also, you have to put the driver also, the software also, hardware also. As you keep on increasing the number of antennas, the complexity and the cost is going to increase. But if the data rate increases 1%, and cost increase is 2 times. Nobody wants to invest. So that is why we have not been able to extract out that much gain from massive MIMO. One way around is if we distribute the antennas. So instead of having all the antennas in the one place, let's say now I distribute them. Now we can't distribute the antennas for phone, but we can distribute the antennas for base station, which is precisely what is happening for 6G, where we are looking at distributed MIMO setups, where we are saying for massive MIMO in 6G, we will not put all the antennas in one base station. We will have 5 or 10 base stations. 5 antennas in each one of them will be used to communicate to one user. So this way you have massive number of antennas, maybe 25, 30, 50 antennas, but in distributed locations, so that the channel is, it doesn't have that high correlation, it's not that dependent with each other, right? Okay, that was one part of the talk. I'll quickly come to the second part. Quick time check. I have like how much? 15 minutes more or 20 minutes? Sure. Because my topic was cooperative communication schemes for relaying in OFDM MIMO, right? So I have already motivated MIMO. Now I'll motivate OFDM A. I'll also tell you why OFDM A and not OFDM. So OFDM is an old technique. OFDM is if you are using an old Wi-Fi device, that uses OFDM. Phone doesn't use OFDM. It uses a multiple access technique which is inspired from OFDM, which is called OFDM A, right? So I'll try to motivate it quickly within the timeline. Now for this multiple access technique, as you see, we have evolved. So how many of you have studied FDMA, TDMA, CDMA before? TDMA you have? In which course? Fair enough. So now as the cellular networks have evolved over past 4 generations, the first generation was FDMA, which was frequency division multiple access. In interest of time, let me use the figure and explain it to you guys. For frequency division multiple access, what we do is we have certain amount of power. We have a certain amount of power. For all time, for a particular user, we give it a certain amount of frequency band. So as you see here in figure B, blue user is getting this frequency band. This is the frequency access. It is getting this frequency band for all amount of time, right? User 2 will get another dedicated band. User 3 will get another dedicated band, so on and so forth. It has its own advantages, by the way. It's a primitive technique, but the advantage is quality of service. Because there is dedicated frequency band, this user doesn't have to worry about interference. This user is a very privileged user. Has the frequency band available for itself. The disadvantage is if you have very large number of users, you don't have that much frequency or you don't have that much spectrum available. To give you context, the most recent auction that happened for 5G, there was an auction recently last year, last year, before these services were launched, right? I hope it's okay to continue. Okay. Before this current 5G services were launched, there was an auction for 5G spectrum. Does anybody remember how much money was paid for it? Yeah, louder. 1.5 lakh crores, right? Now, out of that 1.5 lakh crore, few hundred crore was paid by one operator for a 20 megahertz band. Just 20 megahertz. Now imagine if that 20 megahertz you can only give to 200 users. Because these are not operators who are doing it out of community service, right? These are businesses. See, telecom operators it's a business. Any operator you choose, they are there to make money. They are not there to do social service. So if I as an operator, I am going to pay 500 crores for 20 megahertz and I am going to have, let's say 100 users there, then each user should pay me how much? Few crores. Are we paying few crores? No, right? Why? Because the same spectrum is getting reused. So we can't have this dedicated spectrum kind of approach. We need to reuse the spectrum as much as possible. Not only reuse it for a user, we should be reusing it for only active users. See, if I am not using my phone, why should a spectrum be allocated to me at this point of time? When I open my phone, when I start using WhatsApp or whatever, that point of time I should get spectrum. All the other time I should not. So it is a function of time. which is precisely what people realized 40 years ago. And they started using TDMA kind of a system, where for TDMA, instead of allocating all the frequency instead of allocating a dedicated frequency for all amount of time, now what we are doing is we are taking all frequency and giving it only to active users for certain fraction of time, right? Which is precisely what is happening here in figure A. User 1, the blue user, is getting all frequency for this much amount of time. Then user 2 becomes active. User 1 is not getting frequency anymore. User 2 is getting for this much amount of time all frequency resources, right? So this is what people did in 2G systems, even in the Indian context. The 2G system typically with TDMA. Please take this with a pinch of salt, because the way 2G, 3G has evolved globally is very different. The way it has evolved in the Indian context, the way it has evolved in the Chinese context, and the way it has evolved in the US context, that our 2G may not be the same as Chinese 2G or US 2G, right? So it's just for our broad understanding. But it has a regional connotation also. If you want, you will have to dig a bit deeper that in India, what was a 2G technology? But for just to abstract it out, I'm saying 2G was a TDMA system. Similarly, we had 3G, which was a CDMA system. Have you studied CDMA already? Code division multiple access? No? Okay. Think of it as follows. You have a very high rate set of sequences, which are orthogonal. So you have a sequence of ones and zeros. And then, how many of you studied orthogonality? Orthogonality. When do we say two sequences are orthogonal? Sorry? You'll have to be a bit louder, sorry. You are at a disadvantage. I'm like a base station with a lot of communication power. You're like a mobile phone, less amount of power. You have to be louder. Yes. Quick feedback, just to understand. 90-degree phase shift, yes. So 90-degree phase shift means orthogonal. Another way to look at orthogonality is if you take a dot product, the dot product will be 0, right? So I can have a long sequence of ones and zeros, where when I take a dot product, the dot product is 0. For that matter, I don't need to take two sequences. I can take a collection of 100 sequences. Each of them can be orthogonal to each other, right? Now if I use these 100 sequences, one for each user in this room, transmit, at the receiver, I take a dot product with one of them, then only the corresponding sequence remains non-zero. Everything else will become 0. This is precisely what CDMA works on. The code is a high rate sequence. You modulate that high rate sequence with your communication signal, and at the receiver, you already know which code you should be listening to. You only decode using that code. Everything else becomes 0, your signal remains non-zero, right? Which is what is highlighted here, that you can have all the frequency and all the time, as long as you have sufficient orthogonality in your code. In this case, I have written power, code, or space, because you need not have code division multiple access. You can have power domain orthogonal multiple access also. You can have space, like spatial modulation we're discussing. You can have spatial domain multiple access also, right? But these are all techniques. So except power and space, code is the 3G technique. It was already deployed in the Indian context. Before current Jio, there was a Reliance company by the other brother. There are two brothers, right? The younger one had a company called Reliance Communications. Reliance Communications had a lot of deployment in code division multiple access based phones, right? And then from 3G CDMA, we have now evolved to 4G OFDMA, which I want to highlight to you guys what OFDMA is. OFDMA essentially means orthogonal frequency division multiple access, where we are taking a certain amount of time, certain amount of frequency, and giving it to a particular user. Like here, in this time, user 1 and user 2 are communicating simultaneously. They're getting certain fraction of the resources. So we are dividing this whole time frequency grid into smaller chunks. We are calling each chunk a resource block, giving a resource block to one user. By the same notion of orthogonality that you discussed earlier, right? The dot product one, even each of these resource blocks are orthogonal. In FDMA, each frequency component is orthogonal. In TDMA, each time slot is orthogonal. In OFDMA, the fraction of time frequency resource is orthogonal. Because you already know a unique point in time and frequency space that your information is available. You neglect everything else, only listen to that part. Another way to look at it is, this is time, this is frequency, each chair is unique. If I write something on each chair and I tell you which chair you should look into, you can uniquely identify that message, because each of them is uniquely located in this time frequency grid, right? Which is precisely what we use in 4G. So 4G phones, they use OFDMA, right? Now where did this idea come from? I'll briefly motivate you. Again, a small mathematical example. Maybe I'll skim through this one in interest of time. So let's start with a TDMA example. A very basic TDMA, because you guys have already done TDMA, so hopefully you should be able to answer this one quickly. For a TDMA system, let's say I have a base station. I have some M number of users. For each user, there is some base rate Ri, where Ri indicates if all the resources are given to this user only, then the link rate is equal to Ri, right? All time, all frequency is given to this user, it will get rate Ri. If it gets 1/10 of time, its rate will be 1/10 of Ri, so on and so forth, right? So again, I am encapsulating a lot of detail in Ri. Path loss, fading, shadowing, all that clubbed together, we are getting one Ri, right? Ri will be different for each user. You can also think of it as, if I am transmitting a signal, each one of you is receiving it. Those at the back may receive less signal. Those in the front may receive more. So distance-based attenuation can be there. Some of them might be feeling a bit sleepy, slouching in the chair. So the chair in front is blocking them. Blockage loss. So various wireless artifacts might come into picture. All of that captured together, we are getting some link rate Ri, right? Now what we want to do is, let's look at it as a math problem. See, at the end of the day in research, we want to characterize it either as a mathematical problem or we want to deploy it and test. Either I prove it works or I show it works. Those are the only two typical ways we do it. In this context, I didn't want to have any demo setup, so I have a math-based setup, right? So now imagine I want to maximize the sum rate for a TDMA system. There are certain constraints. The constraints are as follows. Each user rate is lambda I, right? Resultant rate is lambda I, where lambda I is equal to alpha I times Ri, where alpha I is the parameter I am selecting. Let's say I am the base station. Each of you is a user. For each of you, I am going to decide what is going to be the fraction of time. That fraction of time, as the name indicates, because it is a fraction of time, it cannot be negative. Because this is not Avengers movie. There is no negative time here. You can't go back in time, right? So fraction of time has to be positive. So alpha I has to be greater than or equal to 0 for every I. Worst case, alpha I is 0. One of you maybe doesn't get any opportunity for data transmission or reception. Also note, total time is finite. I have, let's say, some number of slots, or in a slot I'm dividing this time. So total time is finite. So maximum fractions, if I add all of them, they can only be equal to 1. So summation of alpha I, it can be less than or equal to 1. It cannot be greater than 1 because time is finite. Also, each user's rate, resultant rate lambda I, is equal to alpha I times Ri, where Ri was the link rate. Alpha I is a time fraction given by this TDMA system to this user, right? One feasible solution is, in this case, let's say each user gets equal time. If there are capital M users, every user gets 1 by m time. Alpha I is equal to 1 by m is a feasible solution. It will not maximize this problem. It will not achieve this objective of maximizing the sum rate, but it's a feasible solution because the moment I take alpha I is equal to 1 by m is greater than 0. So third constraint is satisfied. When you add 1 by m summation I equal to 1 to m, it is m by m which is equal to 1. So summation of alpha I will be equal to 1. So second constraint will also be satisfied. But of course, first constraint will be satisfied because lambda I is 1 by m, alpha I is 1 by m, so you're substituting that, so lambda I becomes 1 by m times Ri, right? But will that be the allocation which will maximize the sum rate? Or is there some other allocation? So here, for this example, let's presume R1 is greater than or equal to R2 is greater than or equal to Rm. So you can also imagine as user 1 is sitting in the front row, then user 2, user 3, user 4. So user m is sitting at the end. So the resultant rate or the link rate for user m is the least. The user very next to the base station, the rate is maximum, right? Now we want to find what is the solution of this problem, right? Again, just like in real life, in math also, always start with a simpler problem. What is the simplest problem I can solve for this? For how many number of users? 1 would be a degenerate case, because for 1, that user gets everything. So that solution, it's difficult to generalize. See, how many of you studied induction? Induction, mathematical induction. I should ask another question. How many of you remember math? You must have studied for sure. How many of you remember? Because it's a school topic, right? You must have studied in school, mathematical induction. How many of you remember mathematical induction? Very good. So mathematical induction, you have to prove it for 2. For 1, it has to exist. You prove it for 2, and then you can generalize it for n by induction. Right? That's one way to look at it. So going back to the context, why I was saying this is, one of you said we can do it for 1 user. That will not be sufficient. If you want to show it through induction also, at least, you have to solve it for 2 users minimum. Only then you can apply induction on top. Right? So now, how to solve it for 2 users? Can you give me a possible solution for 2 users? So if you have 2 users, alpha 1, alpha 2, R1 is greater than R2, what should be the value of alpha 1 and alpha 2 such that alpha 1 R1, because lambda is nothing but alpha Ri. So alpha 1 R1 plus alpha 2 R2 should be maximized under the constraint that alpha 1 plus alpha 2 equal to 1. This you should be able to solve. Or try to solve. So alpha 1 plus alpha 2 equal to 1, and you want to maximize alpha 1 R1 plus alpha 2 R2. Another way to solve it is, you substitute alpha 2 is equal to 1 minus alpha 1. So it becomes alpha 1 R1 plus 1 minus alpha 1 R2, right? Which is equal to R2 plus alpha 1 times R1 minus R2. Is R2 a function of alpha? No. It's a link rate. It's the resultant rate you are getting, irrespective of what time fraction you are getting. Plus alpha 1 times R1 minus R2. Now R1 minus R2, is it positive or negative? Based on this. R1 minus R2. Positive quantity, right? So if you look at it, R2 plus alpha 1 times R1 minus R2 is the equation of a line with a positive slope. More the value of alpha 1, more will be R2 plus alpha 1 times R1 minus R2. What is the maximum possible value of alpha 1? 1. So the solution for 2 users is, for this particular example, is alpha 1 should be equal to 1, alpha 2 should be equal to 0. Right? Because we are maximizing the sum rate. Now by induction you can generalize it to m users also. If you have m users with these kinds of link rates, the resultant solution will be alpha 1 should be equal to 1, all the other alphas should be equal to 0. Right? Which is precisely the solution people would have used in a 2G context, because TDM is a 2G technology. But then there is a catch here. The catch is, if I use this solution in practice, then the user sitting next to base station gets all the time. All the other users get 0 time. Would you pay for such a service? No. So people came up with the concept of proportional fairness. What has changed here? The constraint remain the same. Why? For any optimization problem, which you are using to model any real world research problem, the constraints are coming from the physical aspect, from the physics. Please note, this constraint is coming from the time, because time cannot be negative. This constraint is coming because you cannot exceed the given amount of time. This constraint is coming because there is a relationship between your resultant rate and the link rate. So the constraints will remain typically the same. The only thing that we are changing is the objective. What do we want to achieve? In the previous example, we wanted to maximize the sum rate, but it is not getting a solution of our liking. So we are saying, okay, that's not a good objective. Let's change the objective. So now we have changed it to proportional fairness, which is, which is maximizing summation of log of lambda I. Why are we doing this? What is log of A plus log of B? Log AB. So if I have log of lambda 1 plus log of lambda 2 up till log of lambda n, lambda m, it is effectively equal to log of lambda 1 into lambda 2 into lambda of m. What is the value of log 0? undefined or tends to minus infinity. So if I'm trying to maximize an objective and I give you a value of lambda I for which the objective is becoming minus infinity, will that ever be a solution? No. So for this problem, we have changed the objective function to make sure none of the lambda i's should be 0. Because if even one lambda I becomes 0, I'll get something of the form log of 0, which essentially means minus infinity, everything else will be greater than minus infinity only. So we are forcing our allocator, our scheduler here, to give at least something to each user, right? Now again, can you quickly tell me the solution? What might be the potential solution here? Start with 2 users. If I had 2 users, alpha 1 R1 is user 1's rate, alpha 2 R2 is user 2's rate. You can substitute 1 minus alpha 1 for user 2. So then log of alpha 1 R1 plus log of 1 minus alpha 1 R2 is what we are maximizing. What is the value of alpha 1 which maximizes it? Sorry? 0.5. Very good. Because you will get essentially a log of alpha 1 into 1 minus alpha plus log of R1 plus log of R2. That other components don't matter. Only alpha 1 into 1 minus alpha 1 matters. So if you have an expression of this kind, alpha 1 into 1 minus alpha 1, where alpha 1 belongs between 0 to 1, it is a quadratic with a peak at half, which is precisely as you mentioned, alpha 1 is equal to half is a solution. You can again generalize this by induction and show all alpha i's should be equal. If all alpha i's are equal, that's your optimal solution, right? And if alpha I is equal to 1 by m, your resultant rate for each user is lambda I is equal to 1 by m Ri, right? Now this proportional fairness for TDMA only, you can also view this as equal resource allocation, because I am giving equal amount of resource, in this case the resource is time, equal amount of time to each user. It is not getting equal rate because each user's lambda I is different. Lambda I is 1 by m Ri for each user. As Ri varies, resultant rate varies. I'll quickly go through maybe one more form. Maybe I'll, in interest of time, I'll skip this one. But now what we can do is we can keep changing the objective and keep getting different kind of solutions. We can actually generalize this. So there is some notion as alpha fairness, where we can tune the value of alpha to obtain corresponding type of objective. We can maximize the minimum rate, we can be proportionally fair, or we can have maximizing the sum rate, so on and so forth. Now, why was this important? Why did I start with TDMA? Because it's very easy to analyze it mathematically. So it's very easy for me to present it as a mathematical problem, motivate you guys that you can actually solve it. Now, in the 4G context, what happened just before 4G was, in Wi-Fi domain, there was a technology called OFDM, which was one of the topics as part of my today's session. What is OFDM? In OFDM, we are using, any knows what's the full form of OFDM? Orthogonal? Frequency division multiplexing. So we are taking multiple symbols, multiplexing them in the frequency domain such that each of those symbols in frequency domain are orthogonal, right? Why are we doing this? I'll briefly motivate. Again, I'll not go into a lot of math because you can analyze all of this mathematically also. Purposefully, I'm not doing that, right? Just to keep it simple. Now there is some notion of delay spread. Anybody knows what is a delay spread? So what happens is when you communicate in wireless domain, you don't receive one copy. So if I transmit, let's say I have a base station, or this is a base station. It is transmitting something to you guys, right? Some wave, some RF wave. It will hit the walls. It will hit the backside of the hall also. What you will receive are multiple reflections of the same symbol, right? You will not receive one copy. You'll receive multiple copies. Now, same is true for sound also, by the way, but our receiver is so advanced, thanks to evolution, we are able to separate it out. There is delay spread in sound also, but that's a different topic. Coming back, in RF, we have these multiple copies coming. Now there might be a gap. These copies, when we receive them in time domain, there might be a gap between the first reception and the last reception. In some sense, this spread in time or this delay in time, you can view this as delay spread. So now this delay spread can be of the order of, let's say, 1 microsecond. Very small amount of time, right? Microsecond, 1 microsecond. But if I have a delay spread of 1 microsecond, let's say I have a data rate of 400 kilosymbols per second. What do I mean by 400 kilosymbols per second? In every second, I am transmitting 400,000 symbols. Or conversely, you take 1 upon that, it will give you a symbol duration. So my symbol duration is going to be 2.5 microsecond. How many of you use Netflix? Very good. Netflix in HD or 4K? Now, do you think 400 kilobits per second is enough for Netflix? It is not, right? So this is an example from an older era, just to motivate. We are not using this kind of data rates now. We are using much higher. If you are going to use higher and higher data rates, the symbol duration is either you have to shrink the symbol duration or you have to figure out more ways to pump in more data, right? But nevertheless, the example is still relevant because 4G at least microsecond is a relevant symbol duration, right? So coming back, if you have 2.5 microsecond symbol and you receive copies of symbols which are 1 microsecond apart, then will there be overlap between symbols? Yes. How much overlap will be there? 1 upon 2.5 into 100, which is 40%. So 40% of your current symbol will overlap with previous symbol. 40% of the previous symbol will overlap with the before that, so on and so forth. That's a very huge amount of overlap. Do you think if I increase the data rate or if I decrease the symbol duration, the situation will worsen? And that is why we don't communicate at very high symbols per second. It's not that we don't have the hardware. We may have the hardware for not only microsecond, we may have the hardware for picosecond also, nanosecond also. But they will all overlap. If they all overlap, how will I know which symbol was transmitted? Right? So this limits our speed at which we can pump in data. Right? One way to get around this is OFDM. What we do in OFDM is, instead of using one single carrier, you have done the analog communications, so you must have studied single carrier communication. So instead of using one cosine with very high omega, we use multiple cosines which are orthogonal to each other. As you mentioned earlier, right, 90-degree phase shift. So instead of 90-degree phase shift, if I give you cosines which are, let's say, some factor of 2 pi f apart, then when I take a dot product, they will all be orthogonal to each other, right? So we are taking multiple such subcarriers in OFDM which are all orthogonal, but because they are smaller in frequency, I cannot pump in very high data rate on each one of them, right? So instead of pumping data at 400 kilosymbols per second, now let's say I have 10 subcarriers. I am taking the same frequency, I am dividing into 10 smaller chunks. So each of those subcarriers will be carrying data at what rate? 40 kilosymbols per second. I have 10 of them, right? At 40 kilosymbols per second, now what will be the effective overlap? For 40 kilosymbols per second, the symbol duration will become 25 microsecond. For 25 microsecond, delay spread will not change because delay spread is a function of the physics. At that center frequency or around that center frequency, by and large, the delay spread will remain the same because the reflection from the wall is same only. Whether I transmit at 3.9 gigahertz or 3.9 plus some 50 or 3.905, it remains the same. So now effectively the symbol overlap will become 4%. And for each of those 10 smaller subcarriers, it is only 4%, but the data rate remains almost the same. Because I have each one of them sending 40 kilosymbols per second, I am still sending 400 kilosymbols per second without this effect of delay spread or intersymbol interference. So this is one way how OFDM enhances performance. Again, there are multiple other advantages also. In interest of time, I am not going into those details or that math. So now what people have done is, people realized maybe 20 years ago that this is a nice technique. Can we pick this technique into multiple access? So what we did was, instead of using just OFDM, people started using OFDM-A, where they said, okay, we'll divide the time and frequency into grid. In frequency, it is individual subcarriers. Because there are multiple orthogonal subcarriers, we'll get the same advantage what we get from OFDM. But we don't have to give all the subcarriers to one user. We can divide it across different users. In some sense, multiple access. In time also and in frequency also, which is precisely what OFDM is all about. Again, a very short example, maybe in 5 minutes I'll wrap up. I know I'm already overshooting my time. I don't want to keep you away from lunch for long. So in this example, let's say I have 1991 as time and frequency. So imagine this as one time slot, second time slot, second user's first time slot, second time slot, and this is the frequency, subcarriers, 2 subcarriers. Again, a very simplified example because in practice we may have 100 subcarriers. Here I am taking just 2. Now what happens is if you're using OFDM plus TDMA, you have to give one time slot to one user and apply OFDM on top. So I can give time slot 1 to user 1 and time slot 2 to user 2, or time slot 1 to user 1, time slot 2 to user 2. Here I have purposefully constructed the matrix such that for OFDM TDMA, the data rate is going to be 0.5 log 1 plus p plus log 1 plus 9p, irrespective of which time slot you give to which user, because they're symmetric. If I give the first time slot, you'll get 1 and 9. If I give second time slot, it will be 9 and 1. Rate will be same. But if I use OFDMA, then I don't have to give within the same time slot. I can say, okay, first time slot, this subcarrier to user 1, first time slot, this subcarrier to user 2. Similarly, second time slot, this subcarrier to user 1, this subcarrier to user 2. The advantage is the resultant data rate will turn out to be 1 plus 9p log 1 plus 9 log of 1 plus 9p, right? So there is a significant enhancement in data rate. Now this is happening because the channel is changing with time and the channel is changing with frequency. So if it is a time selective, frequency selective channel, then we'll get gain in OFDMA. If it is a flat channel in time and frequency, both will give same performance. But in practice, it is not flat because either we are moving, the target is moving, or something in the environment is moving, right? So we can do this at a larger scale. This example is from Wi-Fi, but just to motivate, we have time, frequency. So this is the OFDM, typical OFDM, where we give in a time all subcarriers to a user. And I have given you the converse example from OFDMA, where we give in the same time slot some resources to one user, another resource to another user, right? We can also model this mathematically. I'll not go into the details, but you can frame it as an optimization problem again, and you can solve it also to a certain extent, where Xij represents the resource in time frequency, Rij represents the link rate in that particular time frequency resource, and again you can optimize. Whatever we have done for TDMA, something similar you can apply for OFDMA also. The catch is, for TDMA, it was a continuous problem. So I could apply, like I could solve the quadratic maximize over alpha. But here it is a discrete problem. These are discrete set of resources. You have to decide which resource to give to which user. So the problem is more complex because now imagine 100 users. For a typical LTE frame, you will have 100 subcarriers and 10, let's say, time slots in one frame. So you have a matrix of size 100 cross 10, 1000 elements. Each element can be given to any user. So 100 possibilities for one block, 1000 blocks. What are the total permutation combinations? Yes? 100 to power 1000. Each block is independent, right? So 100 for first block into 100 for the second block, 1000 blocks. So 100 to power 1000. That is a very complex problem to solve. But imagine it is already being solved. For past 10 years, all 4G base stations that are deployed in the market, they are solving this real time. Right? So there are techniques available to solve this. Just to motivate you guys to OFDMA. So we have covered MIMO, we have covered OFDMA. I have I think 2 slides remaining. I'll skim through the relay part because I think there are a lot of others who are going to speak about relay. So I'll not go into that direction. So you can have different types of relays in practice. You can have single antenna relays, you can have multiple antenna relays. Yeah, I'll focus on this and then just one slide to go. The key part is whatever we have discussed for OFDMA and MIMO, now you can also have a relay in between. And you have to redo the whole math. So we discussed certain amount of multiple access, we discussed certain amount of MIMO, right? Now imagine a relay in the loop where I am communicating first to the relay and then the relay is communicating to the receiver, or I am also parallelly directly communicating to the receiver, right? So you can further make this problem more and more interesting. Again, relay is a topic just like MIMO, which is very well researched. Same 1000+ papers, few hundred PhDs have graduated in this domain of relay only, right? But there is no practical solution available for it. By practical, I don't mean a prototype or a solution. People have designed solutions. They work also.
but they are not commercially deployed. You will not find a lot of relays deployed in practice. Mostly you will find people will deploy a small cell. So you will have these macro base stations, these towers, and then if you go to Gachibowli and those places which are more congested, you will see these smaller base stations. Because it's always easier to reuse the spectrum than to relay the information and not reuse. Because spectrum is the costliest resource at least in the context of cellular networks, as you guys rightly mentioned, right? Few hundred crores. If I'm going to spend something, that much amount of money on something, let's say few hundred crores, I would like to reuse it as much as possible. And that is why in practice, people typically go for small cell based solutions and not relay based solutions. I'll briefly highlight where this is headed, just to give you an overview from research perspective. So now over past 5-10 years, another technique that has evolved is IRS, which is intelligent reflecting surfaces. How is it different from relay? See, in relay, what happens is either you listen, decode the information, and then communicate it forward, or you receive the information and amplify it forward. And there are multiple other techniques also, which I'm not going into details of. But the catch is relay needs to have processing power, right? It needs to have some transmission power also, or amplification power also. The moment you have any such active element in the relay, it becomes costly. And if there is cost involved in deployment, also please note, for any such deployment, you need power supply and you need to pay rental. So it becomes a costly affair to deploy such relays in the market. That is one of the prime reasons why as a technology it is available. It's not that relays are not available. Relays are available, operators are not deploying them. So it's a reasonable technology, it's a good technology, but not cost effective. IRS on the other hand is a competing technology that has emerged in past couple of years, where we are saying, instead of deploying a relay, we'll deploy a surface, a reflecting surface, which is intelligent in nature, consumes minimal amount of power, right? Has multiple small elements, so you can do MIMO on top. Whatever we have discussed for OFDM and MIMO, you can apply that on IRS also. So effectively you replace this with a surface, a meta surface, which is intelligent, programmable. Runtime, you can tune it. So for example, for this room, if you want excellent coverage at the back, maybe we deploy 2 reflecting surfaces on either side of the wall and then tune them so that certain components from them through beamforming, which we discussed in the beginning, are at the back, certain components are in the center, certain components are in the front. So that way we can try to cover a much larger area using a reflecting surface. You have to still program it, but you can do that once and then let the surface be. You don't have to tune the surface again. For this kind of an environment, a one-time deployment may suffice. So which is why a lot of work is happening in the domain of IRS. I've already described massive MIMO setup previously, so I'll not go into the detail of that. I think you remember the distributed MIMO part, right? From the multiple access side also, maybe just to highlight, this is the last technical point from my side, sorry. From multiple access side, people are now talking about non-orthogonal techniques. So for up till 4G, all the techniques are orthogonal techniques. TDMA is orthogonal in time. FDMA is orthogonal in frequency. CDMA is orthogonal in code. OFDMA is orthogonal in time and frequency. And now we are talking about NOMA, which is a non-orthogonal multiple access. The understanding is if you have sufficient complexity at the receiver, for example, I am talking and some of you are also talking parallelly, right? Your human receiver is able to process what your neighbor is saying by cancelling what I am speaking. I am at much higher power. If you look at it in the hall, the amount of signal power that I have is exponentially larger than your neighbor. But because you are sitting close to your neighbor and my voice volume is high, you can easily understand what I am saying. Your ear is smart enough to cancel it out and then hear what your neighbor is saying. Like, you know, this is called successive interference cancellation. And this has been adopted into communications now. So for 5G and beyond, people are looking at SIC based multiple access. NOMA and RSMA are those 2 techniques. Non-orthogonal multiple access is one of the key ones, and then RSMA is also there, right? So in our group, we are working actively in all 3 of them. So if any of you is interested, please do let me know. I'll quickly conclude. That's my email address. If you are interested to work on a project for a summer internship or anything technical in nature, do feel free to contact me. There might be a turnaround time, but I'll do respond to your email. Briefly, in 30 seconds, I try to highlight about my department. So I belong to the Department of Electrical Engineering at IIT Hyderabad. I am also associated with the AI department at IIT Hyderabad. For both the departments, we are actively looking at grad students. So if you're interested to pursue masters or PhD, please do consider us. We are ranked, I think, 8th this year in NIRF in engineering. We are ranked 3rd across India in innovation. Even better than some of the older IITs, right? So from a place to do research, we are doing reasonably well. In terms of the stipend, if you pursue a master's, the minimum stipend you get is, I think, 12,400 per month. You can get much higher stipend also. For example, any student who is pursuing a 3-year master's in my group is getting around 25,000 per month, which is reasonably not bad as a student, right? If you pursue a PhD, you get minimum 37,000 now per month. It can go up till as high as 80,000 also with Prime Minister Research Fellowship. So in my group, out of 6, there are 2 PMRFs. So again, it's a reasonable amount of money. Also, if you're looking for a job, the kind of job opportunities that you have post-masters and post-PhD, at least from IIT Hyderabad, they're going to be reasonably good. So because I am the current placement in charge for IIT Hyderabad, I can share that. So from placement perspective, for our masters in communication and signal processing, the average package is around 20 lakh plus. For PhD, it will be even higher. So if you invest those 2 years, 3 years, 4 years for a 2-year master's, 3-year master's or a PhD program, you may get a quantum. I'm not familiar with what is the current average package here. Maybe it is comparable, I don't know. But I just want to highlight that it's a reasonably good opportunity, at least to pursue. The only requirement is you have to be GATE qualified. You need to qualify GATE. If you have higher GATE score, you can get direct admission to the 2-year MTech, MHRD funded. If your GATE score is not very high, but if you still have a qualified GATE, you can apply for a 3-year program, an MTech RA program in IIT Hyderabad. The additional year is actually better because you get to work on more problems. You get to do internships, a lot more internships in the industry. So there is a trade-off of time, but you gain a lot of exposure in that 3-year masters. The average package for 3 years masters is slightly better probably, or comparable to 2 years master. It's not lower. And you can still pursue a PhD. You are also allowed to directly pursue the PhD program. If you are interested, just after your BTech, if you have GATE qualified, not even a high GATE score, GATE qualified with reasonably good PTech percentage, you can also apply directly for our BTech entry, direct entry scheme. And you can get into MHRD funded or project funded PhD. Again, there, if you join us directly out of BTech, you essentially get both the degrees. So it's a dual degree program. You will get a master's and a PhD once you graduate. If you're not happy, you can graduate with a master's also, for whatever reason, if you don't want to pursue the PhD, right? So please consider, if you have any queries, if you have any comments, do reach out to me. I'll be happy to answer them. And hopefully I look forward to see a couple of you at least in our campus in a couple of years from now. Thank you. Sorry for the delay from my side. Sorry.
Any questions? Thank you, sir. Actually, you have explained the access techniques in such a most simplest possible way that they could have easily related to the practical examples that you were giving. That's how the access techniques is taken over in the communication stream. And I hope the last 1 minute that you have taken to describe about IIT Hyderabad, few of you would go and consult sir, and probably you will go with your masters or you will do some research in the same area, and we can see you in IIT Hyderabad. So thank you, sir, for taking out time and interacting with our students. I request Rajendra sir, Dean Academics, to felicitate Abhinav Kumar sir, and I request Satish sir to join him.